Hey, hi, hello. Okay, if we can be heard, he's Levente, I'm Ernő. We are all the way from Hungary, as you have heard, and we have brought you some experiments to measure energy. We have been told that we have a lot. We move around a lot, we do stuff a lot, I guess, and we want to know how much energy is way too much energy and how much energy is not that much energy, so we can compare our energy to our colleagues or some experiments or something. So, what do we have first, Levi?
The first experiment might be familiar to those of you who saw it in school. It's a Van de Graaff generator. It basically creates high voltage by depositing positive charges on that globe and all the negative charges into Earth and that smaller globe. It basically creates sparks. Like that. Those aren't that big ones now, but they are sparks.
It's kind of impressive, not so much impressive. I mean, you can decide. Some of you might have seen it. What we want to do, we want to measure the energy in one spark. We need some things to do. I mean, some of you might have, I mean, most of you probably have studied some physics. So what you see there, some of it is behind the big globe. But what you see there are some equations from high school, probably. And we are using that to measure the amount of energy.
What we need is actually a capacitor to store the energy, because what's on this globe is a little hard to measure. So I'm going to be what the charges will be deposited on. For that, I just have to touch the globe and be insulated because the board is wet and I don't want a shock. So let's see what happens.
Are you positive you're charged or you need some more time?
I think it's good.
Okay, okay. Are you ready? Do you want me to shock him?
Ow!
All right. How satisfied are you with this?
Well, I'm in pain, but I think it's going to be okay.
That's on you.
So what we have here is actually the discharge of the spark that we just measured. What we needed to measure was the voltage across a set resistor. The voltage we had can be read from the oscilloscope. It was, you can see here, one step is about 10 volts. But we have a 10 times multiplier on this little switch here, so each is 100 volts. From the bottom to the peak, it was a little over 1, 2, 3, so we'll say about 325 volts, but we need the time it took. We're just going to use the triangle method for an easy average, so we're just going to half it. So what we had is 325 volts, 325 volts.
Right.
325.
Sorry.
Our resistance is 0.0015 ohms, and you can see the time there. It's 47 nanoseconds. That's a very, very short amount of time. And you can see we had, oh, that's half that, so it's about 100 and, I don't know, 75-ish. Sure. That gives us about 0.9 joules of energy, barely under a single joule. Is it much?
I have
a spark.
No idea.
We have no idea, so let's just move on a bit and experiment a little. So we have a scope yes. Of what's a lot.
We need something to compare it to. So we have a kinetic experiment. We are going to shoot something. It might or might not be a bit loud. So when we say be prepared to cover your ears if you are afraid of sounds, not just yet, we need like a minute or probably not that much.
What we have here is a big tube. That is a vacuum pump. It's going to suck all of the air out of the tube. This is the end plug of our so-called cannon. We're just going to aim it here because I don't want to hit anybody with anything. If that's turned on, it's going to try to suck out all the air. And when I release it by knocking this off, it's all coming back at once, which accelerates this tiny ball to very high speeds, very fast, and it's going to get a lot of kinetic energy. Let's see. So we're sucking out the air. You can see the tiny gauge. Well, not now.
You can see me trying to gauge what the pressure is inside.
It's probably fine by now. So let's do a countdown.
Okay, cool.
Let's do a countdown. 3, 2, 1. Oh, it was a bit loud, I know. We didn't shoot the ball, but I think that's better off because this was an experiment we've done in our science center, and you can see the video we took. It's a slow motion video, and we calculated the speed from that. You can see the ball over here. This is a meter, and that's how much time it was on. It was 32 times slower than real life, and it was still way too fast to even see. That's why I had the arrow over there. So the real time that it took to travel a meter is 0.018 seconds. That's, again, a very short amount of time. If Ernő just opens up a calculator...
No. Use your head.
If Ernő just opens up a calculator and divides 1, because we had 1 meter, by 0.018 seconds, you get 55.5 meters per second. He can write that into our little equation chart.
Oh, okay.
55.5, and the mass, that was a piece of plastic, the mass of which was about 12 grams, so 0.012 kilograms, which is 18 joules. So we're already an order up from about 1 to something with 10-ish, or the tens of joules of energy. Oh yeah, we have
had
it
about
on there.
1 joule. Now we have about 19-ish joules. It's higher. Is it much though?
No, yes, no.
Not much. Not
Much.
Right.
Okay. We
Not
have
enough.
some more. We're only at half. So we call that, not that. Oh yeah, the wire atomizer. We're going to put a lot of energy through a tiny piece of wire. I'm just going to set it here.
Sure, that makes more sense.
This ominous white box contains, definitely doesn't contain, the insides of 2 defibrillators.
It never did and never will.
Yeah, it never did and never will. But if someone has friends at the right places, it's easier to get their hands on this. If I press this button, you can see the light lights up. That's a current limit, just so we don't trip the breakers.
We already did start something.
Yeah, we already did start something. You can hear it in movies like charge to 300, charge to 600. We're doing just that. Like, this is the action that they say charge to 600 or 300. Our capacitance, I'm just going to say it real quick until it charges. Our capacitance is 2,760 microfarads. We have measured that. We have also calculated it. And the voltage is going to be about 620, 30. Let's say 30. 630 volts. 30. 0.
I mean, it's still going.
Okay, then it'd be 40. So that's going to be 565 joules into this tiny piece of wire. And this is about the time that I put up a second pair of glasses. So 640 it is. This is loud again, but spectacular. So open your eyes and close your ears.
Let me just get some distance.
So 3, 2, 1.
All right.
It seems we didn't have a big enough piece of wire because, as you can see, there's still 260 volts there. But the wire is not here. As you could see where it went about all around the place. And that was the release of, well, not all 600 joules or 560, but most of it. Yeah, you can see the equation there, half a C times U squared. I don't think this is enough. Was it enough?
Nope.
No!
It wasn't enough. Okay.
All right.
For the last part, what we didn't mention yet, I think, is that one of us knows chemistry a little more than the other. That's Ernő.
I'm supposed to.
He knows chemistry a little more, but he also likes sugar. He likes candies. That's why he has some gummy
Courtesy
bears.
of our Bulgarian friend, somewhere around there, based on the sound he emitted a second ago or a minute ago.
Yes, that sound. Thank you.
So, we have the gummy bear. We need something to react it with. If you have been studying some chemistry, you might or might not remember some equations looking like this. This is sugar reacting to potassium chlorate. This is mostly sugar, and the white powder there is definitely potassium chlorate. We do need some energy to kickstart the reaction. That's what Levi is doing at the moment. And we will just use this very, very brave little gummy bear to dump in the potassium chlorate and just see what happens. Again, you might or might not have seen the experiment. We do want to do some calculations, so we know how much energy, pretty much how much energy is released during the reaction based on the mass of the gummy bear that we will measure in a second or right now. Okay.
In a second.
In a second. Cool.
In a second.
Cool.
We assume that every gummy bear is made equally.
Which is probably true.
Which is, yeah, it will be true. It will have to be true. I think this is... Okay, I don't think you can see it, but it's 3.5 grams. It's 3.5 grams. It's a little too... Oh, you can see 349.
Are you ready?
Yeah, I think we're ready. So the brave gummy bear goes for a swim.
And we'll keep it there, just in case. This is fat. You know what?
Don't.
Safety, right? It will go in there
No, it
at
won't.
some point, or not. Okay.
Half the gummy bear.
We'll definitely, very scientifically, halve the gummy bear and just make it go in there.
Okay, he doesn't go for a swim. Okay, anyway.
He definitely will go into the first swing. We just have to be adamant about it.
You can see the gummy bear is swimming in hot water.
Definitely water.
Yeah,
Nope.
definitely water. This is what you would call a hybrid rocket fuel. Like this, you have a liquid oxidizer and a mostly solid fuel. It's becoming less solid as I speak.
Oh boy. All right. Time is very much up, so let's summarize this up. We have a gummy bear. How much energy does 100 grams of gummy bear contain?
According to the label, it contains 1,400 kilojoules per 100 grams.
Something like that. All right. We may or may not have checked that 100 grams of gummy bear contains 46 grams of sugar. So based on those equations, we can calculate from the equation or from the proportions that it's about 12 or 13,000 joules. I mean, we had somewhere like this. We had like 500 is like 1,300. That's a lot. And that's all we have. If we calculate Levy's daily energy intake based on his 75 kilograms, we can see that it's like, what, 300 kilojoules. Yeah, see, 300,000 joules that he uses in an hour.
Just to put that into perspective, you can see here how much time each experiment would let me live if I lived off the energy there. What's interesting is a daily intake for a human based on my weight is 84 million joules. That is 130 times less than what's in a lightning, but it would only let the Genevan pumps that create the water fountain run for 8.5 seconds. That's just to put the energy into perspective. We hope we could show you some of our energy. You're welcome in Hungary. We'll be waiting for you there, and thank you for your kind attention.